Hello viewers, welcome to Obukoniswa's tutorials. I'm Sir Amos, and today we want to look at exact differential equations. Exact differential equations. Now when we talk of exact differential equations, what do we mean? A differential equation is said to be exact if the differential equation has matching partial derivatives, or if certain parts of the differential equation have matching partial derivatives. So by partial derivative, we mean that if the equation is a function of x and y, then we can differentiate f with respect to x whilst we keep y constant, and then we differentiate f with respect to y whilst we keep x constant. So when we are able to differentiate one and keep the other one as a constant, and we differentiate and keep the next one as a constant, then we refer to that as partial derivatives. So how do we solve exact differential equations? To solve exact differential equations, what we do is we obtain a potential function that satisfies the equation. So we obtain the function f such that its partial derivatives will also equally satisfy the differential or the exact differential equation given. And so let's suppose that let f of x be the potential function such that so if this is a potential function whose total derivative is equal to what? 0. So we say that the total derivative of this particular function, which is what? So let f of x be a function such that the total derivative of this function is equal to what? 0, or the total derivative of the function is given as, so we have the f to be the total derivative of the function to be equal to del f del x, then dx, plus del f del y, then dy. So from this side, this is the partial derivative of the function f with respect to x, and this is the partial derivative of the function f with respect to y. So when we put half plus half, that is a partial derivative plus a partial derivative, then we obtain the total derivative. So we suppose that the potential function f has a total derivative given to us as this. And now, so if we let the partial derivative of f with respect to x, that is del f del x, to be equal to the function m, which depends on x and y, and del f del y to also be equal to the function m, which depends on x and y. Then we now have the total derivative del f to be equal to, this side has now become m, so it can be written as m xy then dx plus m xy then dy. So we have m xy dx plus m xy dy. And so we have seen that this particular equation has now assumed the form of an exact differential equation. So we can suppose that the total differential of this particular function is what? 0. So if the total differential of the function f gives us 0, that is, if we combine this and this, and it's equal to 0, that is, to have del f which is equal to mxy then dx plus mxy dy to be equal to 0. Then the function is exact. Exact. So that is to say that the exact differential equation is of the form mxy dx plus mxy dy to be equal to 0. So we have a partial derivative, we have another partial derivative. So when we put the two partial derivatives, multiply dx and dy, then they give us 0. So if the equation is given in the form of this, then that particular equation has become what? Exact. So we can rewrite this as, or regrouping the terms, we can rewrite this one as, if we have mx y, then y prime plus mx y, then to be equal to 0. So at this point, we have decided to what? To divide both sides by dx. So if I divide both sides by dx, then the exact differential equation now has the form m times y prime plus m to give us what? 0. So this is the form or the general form of the exact differential equation. So now the equation will be exact on the condition that we have the partial derivative, that is the m, with respect to y. So differentiating the m with respect to y, and it is equal to differentiating the n with respect to x. So if the n function is differentiated partially with respect to x, and the m function is differentiated partially with respect to y, and then the two are equal, then we say that the particular equation is what? Exact. So that is from here. We have represented this as m and this as n. So if we take the partial derivative of both m and n, and then they give us, or the two are the same, so we say that the exact equation, or we say that the particular equation is what? Is exact. So we can equally write this, or for easiness of writing, we can say that if we have my to be equal to nx, then the equation is what? Is exact. The my means we differentiate m with respect to what? Y, whilst we keep x constant. So that is a partial derivative. And the nx means we differentiate n with respect to x, and then we keep y constant. So that is the partial derivative with respect to what? To x. So if these two are equal in a given equation, then we say that the equation is exact. So having known that this is the form of the exact differential equation, how then do we solve it? How do we obtain the solution to this? So as I said initially, the solution to this one is a potential function. So we want to obtain a potential function that satisfies the equation. So now, knowing we know that the derivative of f with respect to x is what? M. So let's use that first condition to obtain the solution. So now, knowing del f del m, sorry, del f del x to be equal to the function m of what? X. From here, we can make f, or we can obtain the potential function f, and that is, I have del f to be equal to the function m of xy times del x. And so, to obtain the f, I integrate both sides. So taking the integral of del f and the integral of m of x of the function m with respect to what? X. Then integrating f with integrating 1. So what it says 1 with respect to f will give us the potential function f. And this will be equal to the integral of the function m which depends on what? X and y with respect to x. So plus the constant of integration k, which is some function of what? Y. So this becomes the potential function that will give us the solution to the exact differential equation. We have obtained the potential function by using the first condition where we said that let the f dx to be equal to m. So if the f dx is equal to m, we can obtain f, which is the potential function, from here. And now what we need is to obtain the value for the k, so that after integrating the m and adding it to the k, we are able to come up with a potential function f, whose total derivative is what? 0. So this is how the exact differential equations are solved. So let's take some few examples to show whether a given function is exact or not exact. Okay, so the first one says that we are so whether the differential equation, which is 3x squared y squared plus x squared dx plus 2x cubed y plus y squared dy is equal to 0 is exact or not. So we want to show whether this particular equation is exact or it is not exact. So as we learned that the exact differential equation is of the form m of x y dx plus n of x y dy to be equal to 0. So if this is the form of the differential equation that is exact, then comparing this to what we have here, it means that we have m. So ignoring the x and the y, we have m to be equal to 3x squared y squared plus x squared. And then we have n to be this. That is the one with the dy, will be n. So we have this one to be 2x cubed y plus y squared. Alright. So we said that for the equation to be exact, then it should have matching partial derivatives. So that means that you see that this m is with the x. So that means we need to now differentiate it with respect to y. So it implies that differentiating the m partially with respect to y. So take note, the one with the x should always be differentiated partially with respect to y. So if I said my m should be what? The one with the dx, then I will differentiate it with respect to what? Y. And so I have differentiating this partially with respect to y. I'm going to obtain now this function. If we are differentiating it partially with respect to y, it means that anything that is not y here is a constant. So in that case, the x squared is a constant, and this x squared is a constant. So that means that wherever we see x, it is a constant. And so to differentiate this, we consider this term and we differentiate only the y squared because the 3x squared is a constant. And so we have differentiating the y squared to give us 2y, and 2y multiplying 3x squared will give us 6x squared times y. And so differentiating the other term, which is x squared, will give us 0 because this one is a constant, the x squared is a constant, since we are differentiating with respect to y. And we have the partial derivative of what? N with respect to x. And so the one with the dy, which we represented as n, that is this one, should be differentiated partially with respect to what? X. And so differentiating the n with respect to x, we are going to obtain. So in this one, we are keeping y as a constant. So wherever you see y, it is regarded as a constant. And so what do? We now differentiate the x. That's the x cube. So differentiating the x cube will give us what? 3 times what? 2. And that will give us 6x. Taking 1 away from the power, we have 6x squared times y. And now, this y is standing alone, so it is regarded as a constant, since there is no x attached to it. And so differentiating a constant will give us what? 0. So we have plus 0. Now, looking at this, we have the partial derivative with respect to y of the differential equation to be equal to this partial derivative with respect to what? X. We have the m dy to be equal to the n dx. And so that shows that the given differential equation is what? Exact. So we conclude that since the m dy is equal to the n dx, then, okay, so this is also equal to what? 6x squared y. The differential equation or the equation is exact. So the equation is exact. So dear viewers, these are just the basic steps to showing that a particular equation is exact. So kindly watch other videos on solutions to exact and not exact differential equations. This is just the steps or the procedure or the guidelines which will enable you to solve the exact equations. So in my next video, I will be uploading it based on what? Solutions to the exact differential equations. And we are going to follow the same procedure we followed initially up to the point where we have f, so that we can obtain the potential function whose total derivative is what? Is 0 to enable us get the solution to the given differential equation. So please subscribe to my YouTube channel if you haven't done that, and then like and share and comment. Thank you.